it must be following. It must be greater than 2.5. Let me write down. The small scale union. I'm going to. Yeah, we talk about small and scale and union. So for small scale union, we can use K or G to describe the crack tip, the field in the crack tip. That means B is the thickness, A is the crack length, and lowercase p is the ligament length. So these three guys must be greater or equal to 2.5 is the Ki and sigma ys on square is about 24 and this is Ry. So this is small scale union. If these three inequality conditions are met, you can feel free to use the K or G to describe the crack tip behavior. However, if either of these three inequalities is not met, and we need to use other things. We will talk about this one later. But today, we are going to talk about this is homework first. So actually, you can look at this table. So this is the table. This is a table. Look at this table. And also this figure. So you have B value, W value, this ratio between A and W. So estimate the failure load for each specimen. Which specimen has a highest failure load? Which has the lowest one? So you need to use this equation. Okay, so use this equation. So you need to take a look at the table. This is for 2.12. Yeah, look at the table. Okay, your table 2.4 and the figure on 2.23. So this is a P and critical. So this one equals and KIC and P and square root of W. And here is F A/W. So you can use this equation to calculate the P critical. P critical we call this a failure load. Is a failure load. So this is this function. So this function is dependent upon what kind of specimen you are using. Okay? Look at the table. Look at table 2.4 and figure 2.23. And you for different specimens, each of these 5 specimens in this, and they are different, and you can calculate the P critical. You understand? Maybe, and you can use the Excel sheet to do this. Okay, Excel sheet just do this is more concise. Bobby.
So I know there's an equation for each FAW for each specimen, but there's also the graph. Could you just do the graph instead of plugging all the numbers into the equation?
The graph is not when you just get the value, prove values from the graph, it's not very accurate. I would suggest use the equations. Equations we call analytical. The graph, but sometimes we are human, right? So sometimes different people select a slightly different material. Different location. Understand? Using equation, okay? Using equation. So this is the first one. And the second one is a semicircular surface crack in the pressure vessel. You can see the pressure vessel. It's 10 millimeter deep. The crack is on the inner wall of the pressure vessel, and is oriented such that the Hoover stress is perpendicular to the crack plane. This is the crack plane. Okay? Calculate the Ki. If the local Hoover stress and internal pressure, assume the wall thickness is less than. So this one we use a disk equation. So use the principle of superposition, okay? Use the principle of superposition. So you can see, and for this case, this is Ki, this is 12.14. We use the principle superposition principle or principle of superposition, the same thing. So you can see the example, okay? Look at the example on 2.5. And for this one, Ki can be obtained using this. And equals lambda S on sigma on P plus P pressure, internal pressure, on the square root on this pi A over this is a Q and F5. So this is lambda S. So this is lambda S. You use this lambda S, and we use this equation. 1.13 minus 0.09 A over C the square bracket. We have 1 plus 0.1 1 minus and sin 5. Square. So this is a lambda S. You can see, okay, for this one, you see, look at the figure 2.19. Okay, you can see, okay, this is the loop stress. We have loop stress, and we also have internal pressure. That's the reason we use this superposition principle. Now, using these two equations, you can just get this answer. We assume phi equals 0, and we just phi equals 0. Phi equals 0 is on the correct. Is along the correct plane. So 2.16 for the 2.16. And so we also use this is the principle of superposition. On 2.16, I'm sorry. On 2.16, we also use this is the superposition. We use the superposition, okay? We use the superposition because we can see, guys. You can see, look at me, guys. We use the superposition. Superposition means that we don't take care of sigma 2. We only take care of sigma 1 first. For the sigma 1, because this guy is oriented by the beta value angle, so this guy, because of sigma 1, and this guy we have sigma k, we have Ki and also K2, right? And Ki is opening, and K1 we call K1. K1 is opening, K2 is sliding. Similarly, if we do not take care of sigma 1 and we only take care of sigma 2, this sigma 2 is also not perpendicular to this correct plane. So also because the sigma 2 alone, we will have Ki and K2. So we just use the superposition principle. Let me give you, okay? Because I love you guys so much. Because we also use superposition. We use the superposition super superposition principle. Superposition principle means that Ki and Ki equals sigma 1 cosine beta square root of pi a. So this is the contribution from sigma 1 and plus sigma 2 cosine 90-degree plus beta, because this is the angles here, and pi a. So this is a contribution from the sigma 2. Right? You understand, guys? So this is sigma 1, and because of sigma 1, this term is because of sigma 2. So these two guys combined, in fact, give us the total Ki, and Ki we call K1. So with that question, I saw you raise your hand. Okay. So this is K1. Also similarly, for the K2. Are you calculate? Okay, I will not give you the answer. You calculate. This is a Ki or K2, and so this K2 and equals sigma 1 and cosine beta multiplied by sine beta, then square root and pi a. And so this is contribution from sigma 1 for sigma 2 and cosine 90-degree plus beta, because this is angle. Okay, this is angle. You need the orientation matters. And multiply sine 90-degree plus beta and the square root pi a. You can see this one and this one, they use the same equation, right? But orientation, you have 90-degree here. So I will give you some little assignment and tell me Ki, what is the Ki value? Tell me the Ki, okay? And just make some comments. And Ki 1, I'm sorry, and tell me 1 and K2 equals 0. Yeah, you make comments. Okay.
Could you also have done this using Moore's circle?
Yeah.
Taking sigma 1 and sigma 2
Absolutely.
as the principal of.
Yeah. Yeah, so this one is equation version.
Okay.
And Moore's circle, you can use it more definitely. Moore's circle is a graphical representation, but here is an equation. Either both of them are correct. Okay. Questions so far? I want you to give me some comments. When this guy equals 0. So this guy, whenever you give me some comments, make some, you can have some insightful conclusions. Dylan.
When beta is equal to 0.
When beta equals 0.
Yeah. Because then
When beta equals 0, no. When beta equals 0, so this guy equals 0, right?
Yeah.
Oh, here is not 0. You agree? When beta equals 0, sine. This is a sine 1, cosine 90 degree equals what?
I think that's 0.
When beta equals 0, when beta equals 0, you have sigma 2. But when this beta equals 0, so this guy is perpendicular, this is parallel to this sigma, the sigma 2. That's a good question. That's a good question. Yeah, you can use that one, okay? What I want you to find is when sigma 1 equals sigma 2. Right? When sigma 1 equals sigma 2, so these two guys cancel each other. You have sense? Dylan, you are very insightful, but that's a good question. But actually, if we have this guy is a flag, So with this guy's contribution will be K1. So this guy as sigma 2 will have sigma, and we will have you're right. You're right. Where's that one? Also, what I want you to tell me is when sigma 1 equals sigma 2, these two gets cancelled. So this is 216. Let's look at 219. 219 you use the equation. Okay, you use 219. Let me tell you. Let's write here. For the 219, for 219 you use equation. Use equation 2.41. Equation 2.65 and equation 2.76, and use this, you can get this is the values. Using stress three modes. Three modes they are LEFM, and then rho n, and finally the third one is strip, and strip yield method. So these three equations corresponds to these three methods. Dylan, do you know where Michael is? Michael,
I do not know where he is today.
is good?
I think so. I think he's out of town this weekend.
Okay.
I don't know if he left already.
Okay. I just want to make sure he is safe and sound. The 2.20 and the 2.20, these are small scale building, okay? These are 2.20 here, and determine the minimum specimen dimension B, capital B, lowercase a, and W required to perform a valid KSE on material. What does that mean? It means that under what condition small scale building is satisfied. Here. So this is the 2.20. Okay? And I will give this one to you. 2.21. So 2.21, so describe a set of, here using this equation, describe a set of experiments you could perform to determine this one for this specimen configuration. I will give this one to you, okay? You calculate the FAW. After you calculate the FAW, let me give you some hints. 2.21. You get this FAW. FAW is a function. I will not write this one. I just give this one to you guys. It's a function of B, E prime. This is effective Young's modulus, and also DC and DAW. So C is a compliance. C is a compliance. C is a compliance. So this one for the geometry of interest can be inferred by measuring the elastic, and you can measure this is elastic compliance as a function of the cracker length. Evaluating this one, you evaluate this, and then insert into this equation. You need to evaluate this one, okay? Evaluate this, then using this equation to get FW. Any questions so far? One more time. For this one, what I want you to do is write this equation, this exact equation, okay? So I told you, so this equation is a function of these three guys. What I want you comment is that, and from here, based on the compliance, you can get the derivative of the compliance with respect to A and W. After you get this value, then you insert this value into this equation, and then you can just design the experiments. You have sense? I will take a photo and post on the cameras, George. Okay? Maybe from that far distance you cannot kind of blur it. I will take a photo and you can just look at all these photos on the cameras. Questions so far, guys? So 22. The 22 derived the grave English results for the potential underling of the through crack in infinite plate subject to a remote tensor. So there are hints. Solve for the work required to close the crack face. Solve for the work required to close the face. The displacement, we can have the crack opening displacement. Displacement it equals 2uy, okay? And 2uy equals 4 sigma young's modulus and square root a square minus x squared. So this is the crack tip. This is x, this is the y. So the incremental closure work, the work done at a point, and it equals d pi multiplied by 1/2 2 sigma uy b dx. 2uy is a displacement. Right? Sigma multiplied b multiplied by x is a force. Force multiplied by displacement, and then 1/2. That is, this is the work. Then the decrease in the potential underling due to formation of crack, and then pi minus pi 0 will be equal to 4 sigma square. Okay, so this is the d pi, okay? So this is the d pi, then the pi equals d pi equals 1/2 these are two here, 1/2 sigma uy, plug in uy here, and 4 sigma e square root a squared minus x squared and multiplied by b dx. Just plug in. So for this one, okay, and you finish this, get the pi. And then after you get the pi, then you use a pi minus pi 0. This is a pi, the pi 0 equals so this equals 4 sigma square b and e from 0 to a and square root a squared minus x squared and dx. So this is finally, so this one turns out to be pi sigma square a squared b and divided by e. So this is actually is agree with equation. I want you guys to derive it by yourself, right? I will just give you a lot of hints. Questions so far? Without any question, and we continue our talk for here. So last time we talked about the small scale yielding, and we then for this mixed mode fracture, you can see. So here is the beta x, y, and if there is another small angle, we have this alpha. This is x prime and y prime. We have alpha. So you can see here, okay. And KIO is mode 1 stress intensity factor 1 beta equals 0. 1 beta equals 0. So we have Ki, this equals KIO cosine beta square, and K2 KIO cosine beta sin beta. And why we have K2 here? Because this orientation. So this orientation, if we just decompose the original stress and in two directions, which is x and y, and we will have a pair in this direction. We have another pair in this direction. So this pair will result in the Ki. So this pair will result in the K2. So this is a crack tip, the stress field, in the polar coordinates for mode 1. The portion of the loading are given here. So this is for mode 1, right? And so mode 1 you can see Ki. So these is 3 stress values. They can be described using Ki, and also R is the distance between the crack tip and the point of interest. And theta is that the orientation between like here. So suppose this is my point of interest. This is my crack tip. I just draw a line here. So this is my R. This is my theta. Right? So also that means this guy's coordinate is described using the polar coordinates R and theta. So if we have R and theta, as long as we have Ki, and we can describe the stress field using 3 equations. The same thing for mode 2. For mode 2, we have this is a K2 because of this is the sliding the K2 the sliding mode. So the stress intensity factor along alpha direction, infinitesimal kink. So for this one, we can use the Ki alpha, right? And we take the derivative sigma yy, and when R goes to 0, and we can use this one. So this is, and what I want you to know is that you just know C11 K1 and C12 K2. And what is the C11? This is C11, which is a function of alpha. The C12 is also a function of alpha. Right? So here, similarly, Ki alpha and Ki alpha. I can use two equations to calculate Ki alpha also. And you can see here are a lot of equations, right? You understand that? You can imagine, without this PowerPoint and how much energy I need to spend and to write these equations. But this can facilitate our communication. Do you guys agree? But what I want you to know is that you need to take a look at this. My bottom line is that whenever there is a chance, and you know where to get these equations and which equation you should use. Okay.
What is alpha? Like it says along the alpha direction, what is?
Alpha is a small kinky the angle. Let me show you. So here, so suppose we have a beta here. So this is a capital beta. This is a beta angle. So suppose we have a small alpha here, a very small kinky angle. Zero kink, is infinitesimal kink. The small, very small, so small crack. You understand this? So Ki and K2 are the local stress intensity factor at the crack tip. The kink. You know kink, right? It's a small crack. With small crack, we call it small. You know, you can see. So this is our bigger crack, right? Bigger crack here might be a small crack. It's a small crack. Small crack. This is called kink. Ki and K2 are the stress intensity factor for the main crack. The lowercase, you can see capital Ki and K2 are the stress intensity factor for the main crack, beta, so bigger crack. Lowercase Ki and lowercase K2 are the local stress intensity factor at the tip of the kink. As I said, kink is a very small crack just near the crack tip of the bigger crack. This is a bigger crack. So here, these three guys, they are they are kinks. Or kinky cracks, just very tiny, the tiny crack. So the energy release rate for the kinky crack is given this. And we just know how to use this equation. The energy release rate for the kink, the crack is given this one. Lowercase, keep in mind this is lowercase, and this is also lowercase, square, and divided by Young's modulus. So this equals Ki square alpha star Ke1, and you can use that one to calculate the maximum energy release rate. Questions so far? This is a kink. This is a we have new concept of kink. Questions so far? No question? That means you are following me closely, right? Is that a fair statement? You are not sleeping, right? You are not either daydreaming. If you daydream now, and you need to spend 1 hour this evening to refresh your memory, okay? That's the reason I ask my students to pay more attention in the class. Be attentive and be aggressive in the class. Then after the class, and before you go to bed this evening, you just take a very quick look at this is the lecture notes to refresh your memory. That's it. And you can learn everything very well. Okay? However, if you are daydreaming now, and then you spend another hour to go through all the lecture notes and all this is a recording, and then you need more time to understand all these things. That is definitely is not a good way for learning. It's just my opinion, and you can do whatever you want to do. So our goal is that we use the minimum time and effort and to maximize our learning. Do you guys agree? Instead of not opposite. Okay, so here is some equations I'm going to go through. So equivalent mode 1 crack. So also this is Bobby, look at it here, this is king.
Oh, okay.
So this is our main crack.
Yeah.
But at the end of this is the in crack, this is the main crack, we have a smaller one, and we call it kinky one. So equivalent mode 1 crack, define equivalent mode 1 crack. Okay, so K, so this is a K equivalent. So this because this is equivalent, where so this equivalent is a lowercase ki alpha prime, alpha star, beta, and A is the crack length, beta is orientation angle, and alpha is the kink angle, and with respect to alpha, with respect to the major one. So Ki alpha is defined as sigma pi A effective, which equals K1 alpha star. Alpha star is to be determined. So you can just plug in. This is the lowercase k1, right? So which equals k11 ki c12 k2, and you just plug in, right? So keep in mind this is a capital. Capital means the is the for the major body, for major crack. So this is also K1. Keep in mind guys, capital K means the stress intensity factor for the main crack. Lowercase k is the stress intensity factor for the kink. You understand that? So this is how we get this A equal. A equal here. A equal means what? A equal because we have alpha here, the small kink here. And how can we take care of this small kink? Using one equation. That's the reason we want to figure out A equal. Definitely, this A equal, this guy's derivation is from how we calculate lowercase ki and lowercase k2. Right? So this is one thing. Local case for the alpha. So biaxial loading. The biaxial loading means that we have for the this is biaxial loading guys. On biaxial loading, so we have sigma 1 and sigma 2. In our exam, no exam. In our homework problem, we have that one, right? So just use the superposition. And biaxial loading, and we use the superposition. And Ki equals Ki0, Ki0 means that the stress intensity factor for the crack for this no orientation. That means the crack is perpendicular to the load. So we have these two equations, right? So this is and Ki and K2. So lowercase Ki alpha and K2 alpha, and we have these equations also and C1 alpha and C11, C12, and C2 and C22. They are given, and we already know that. And then G is a G, and I will get this G, let G, and we let dg d alpha equals 0. Then we can get this alpha star. Alpha star is the maximum energy release rate. Do guys to remember how can we get the minimum value for some expression? And we just take this expression, take the derivative of this expression with some commutative, and then let this guy equals 0, right? So this is, and we can see g is a function of alpha, and we take the derivative of g with respect to alpha, and then force this guy to get to be 0. Then we can get this alpha star. Alpha star gives us the maximum energy release rate. What does it mean? It means that so this direction is the most possible direction for the crack propagation, because in this direction the energy release rate is maximum. Right, guys? Lucas agree? Okay, so this is the biaxial loading. you can see based on different beta value, also the b value, with b value is also important here. So coplanar cracks. What is the coplanar cracks? Coplanar cracks means that we have a pattern. We have a pattern. Okay? We have a pattern. We have a crack here, and then we have a crack here, we have a crack here. And how can we calculate this guy's Ki? And we use this equation. We use this equation. Was 57 to 58, general principle that multiple cracks in the same plane have the effect of magnifying Ki in one another. So they have magnifying because this guy's existence and so the crack tip Ki will be high. So this is the coplanar cracks. The parallel cracks. So the parallel cracks. So this, you can see, these are parallel cracks. These are coplanar. These are parallel cracks. For the parallel cracks, the cracks tend to shield one another, which results in a decrease in Ki relative to the single crack case. This is indicative of the general case where two or more parallel cracks have a mutual shielding interaction when subject to mode 1 loading. Consequently, multiple cracks that are parallel to one another are of less concern than multiple cracks in the same plane. You have sense? We have two case scenarios. One is the coplanar, one is the parallel. The parallel cracks, they help each other. They strengthen each other. You have sense? However, for the coplanar cracks, and because the existence of the neighboring crack, so this guy's crack tip is usually magnified. That means it's bad for the material. I want you guys to know these facts, right? Also, you can use these facts and for your guidance when you select the material. When you select, make some comments about this coplanar or this is the parallel cracks. Which one is bad? Which one is good? Okay, so this is our lecture 10. Let's look at we have 3 minutes. Let's continue our talk about this is lecture 11. And for lecture 11, guys, so we are going to talk about elastic plastic fracture mechanics. It means that in this under these conditions, in some case scenarios, the LEFM does not work. When LEFM does not work, last time we talked about the small scale yielding. SSY stands for small scale yielding. If the small scale yielding is no longer valid, linear elastic fracture mechanics fails. Okay, so you will need to use other series to do. So how to do that? We have several ways. One is called crack tape opening displacement. So we cannot use K and we cannot use G. We need to use crack tape crack tape opening displacement. So Dr. Wells in 1960s. Dr. Wells proposed this one, guys. So from table 2.2, the UY, okay, this is UY. Let me draw something here. It's a crack. It's a crack. What? It's a crack tape. And so here and here, the displacement of these two guys, and they will be 2 multiplied by UY and with respect to X. You understand? So here, suppose this is my X, so this is my Y, and also here this is a sharp angle, okay? And for exaggeration, I just make it big, but it's sharp angle. A sharp angle means that, so this angle and this angle equals theta, and theta equals pi. So this angle and theta equals minus pi. You can see for table 2.2, Uy, the displacement when theta equals pi can be obtained using this equation. I'm going to stop here now, and next Monday we are going to continue our talk. So when can you finish the homework 3? Next Monday or next Wednesday? I'm okay. I want well done.
Wednesday.
Huh?
Wednesday.
Wednesday? Okay, so Wednesday good. So for the especially for 2.22, I want you to derive this pi, okay? Derive this guy and tell me something. I